Now let's see graph based protocols. See, there are two reasons why we go for this graph based protocol. One thing is, whenever we use any locking, it is also based on locking only. Whenever you use locking, the problem is deadlock, right? And we have to avoid deadlock in two ways. So one way is, if we can break that condition of hold and wait, you can avoid the deadlocks. That is what we have seen already. And the second way is, if we can order the resources, if you can provide some ordering between the resources, and if you can enforce the process or transactions to ask for the data items in that order, then you can avoid deadlock. See, what I mean to say is, see, why do we get a deadlock? Let us say there is transaction Ti and then there is transaction Tj, right? Now we get a deadlock when A wants a lock on A, Ti has a lock on A and Tj has a lock on B, and again if Ti wants a lock on B and Tj wants a lock on A, when these two locks are still with Ti and Tj, we are going to get a deadlock, right? Which means the order in which this one is requesting is some order, and the order in which this one is requesting is other order. Now if we can make sure that all of them request them in the same order, then there will be no problem of this deadlock, right? Therefore there has to be some ordering between the data items. If we can maintain that ordering, and if we can, every transaction can obtain the deadlocks, locks only in that orders, then we can avoid deadlocks. And the second thing is, we want to see that the transactions are, once you finish the transactions, all of them fall in a schedule in such a way that it is serializable, right? Now these two can be implemented using graph based protocol. I'll read out about it. See this. Even though the name is graph based protocol, it is implemented as a tree protocol. So which means, even though the name is saying that it is a graph protocol, what we actually have is a tree. Right? Why do we have a tree is, we don't want cycles, because cycles are the main reason to get the deadlock, and it is going to spoil the ordering. That is why we are going to go for a trees. So I mean to say, it is going to, your data base is going to be arranged like this: A, B, C, something like this, right? You are going to have a kind of tree like this. Okay, now it is the directed acyclic graph known as database graph. So whatever graph you have, it is a tree which is directed. Directions will be from top to down, and it will be acyclic. There will be no cycles, and it is also called as database graph. Now advantage is, we can completely avoid deadlocks. So by using this, we are going to avoid deadlocks. I'll show you how. In tree protocol, the only lock instruction allowed is exclusive lock. So we have only exclusive locks here, and each transaction Ti can lock a data item at most once. So only once you can lock the data item, and following the below rules. Some rules are given here. Now see this: the first lock by Ti may be on any data item. So whenever you take the first lock, that can be anywhere. Either you can lock at the root, or you can lock at B or C or D, wherever. But then subsequently a data item can be locked by Ti only if the parent of the data item is currently locked by Ti. So what it means is, let us say if Ti has locked initially data item D, then later it should not lock data item B. But in case if it wants both B and D, then it should first lock B, then only it is going to lock D. By writing this rule, you will make sure that whenever a date, you need a sequence of data items, you will always start from the top and then you come down. So which means some ordering in which you are going to ask for the locks is going to be maintained. Now if everyone is going to follow that order, there will be no deadlocks, isn't it? There will be no cycle and no deadlocks. Got it? Okay. Now data items may be unlocked at any time. So unlocking can be done anytime. So it is not like you are going to have two phases. So you can unlock anytime, and you need not even wait till commit, right? And then a data item that has been logged and unlocked by Ti cannot subsequently lock by Ti, which means once you have logged and unlocked, don't ask it again. That is the meaning of it. Okay. Now let's see the example here. Now find out whether this particular schedule is following whatever rules we discussed there. Now what is the rule? So you can start off with any node, but then once you start with that node, you are not supposed to ask for a parent of that. Okay, now let's see this. Now initially T1 is asking for lock on B. Yes, lock on B is allowed, and then after B it is asking for E. Yes, you can get E because its parent is already locked, and after that it is asking for D. Yes, you can get D because its parent is already locked. Now it is unlocking B. Yes, you can unlock B, and then it is unlocking E. You can unlock E, and then it is locking G. Right? See, you can lock G because D is already locked and it is still there, and now it is unlocking D. Yes, now if you see the order, you are not asking for a lock without having a lock on the parent anytime. Alright, but then unlocking can be done any way. Either you can unlock the parent or child, it is not an issue, but then only requirement is whenever you are asking for a lock, you are supposed to ask for a lock only if the parent is already locked. Okay, now let's look at transaction T2. Now D is locked. Yes, D is locked, and after D, H is locked. Yes, after D you can lock H, and then D is unlocked. Yes, that is unlocked, that can be done, and again H is unlocked. Yes, not an issue. So you are going to lock and unlock in such a way that always parent is locked. And here it is starting with B. Yes, it is starting with B here. Okay, now after B, E is being locked, right? Yes, after B, E can be locked, and after that E is unlocked and B is unlocked. Yes, unlocking can be done in any way. Fine. So now if you observe this, if any schedule follows these rules, you can clearly prove that all those are going to be conflict serializable. So if you want to see, we can draw the graph and we can find it out. Now let's say I want to draw the graph and see whether it is conflict serializable or not. I am trying to draw the precedence graph. Now if you see precedence graph T1, T2 and T3, let's see where the conflicts are. Now B is being locked, so whenever it is exclusive locked, you can assume that it is being locked for write operation. Therefore every exclusive lock is going to be a conflict with other transactions exclusive lock, given that both are locking the same data item. Now which means if you look at B, if there is any other transaction which is having lock on B, it is going to be a conflict. So if you see this, clearly there is a conflict between these two. Got it? So which means T1 and then T3 is the order, right? Okay. And then if you look at D, yes, there is a conflict between these two. Therefore T2 and then T1, right? Okay. And if you look at H, there is no transactions with H here, and there is no transaction with H here. Okay, fine, that is over. And now if you look at E, there is a lock on E here. It is also saying that T1 and then T3. Yes, not an issue. And then D, log D. So if you look at log D, here only this is the one, nothing else. Okay, that's it. And if you look at G, nothing else, that's it. And then if you look at B, it is over. If you look at E, it is over. That's it, right? So if you look at this, this is the graph, precedence graph. Now precedence graph is clearly showing that there are no cycles, therefore it is definitely conflict serializable. So any schedule which is going to follow the rules that we have discussed till now is going to be conflict serializable, as well as it is deadlock free. Okay, fine.